Hello, my name is Kyle Teskey, undergraduate student in mechanical engineering at Cal Poly San Luis Obispo, and I'm working with manufacturing engineering student Griffin Glenn to complete our project, the design and manufacture of a composite backpack frame. The proposed problem for which this project aims to create a solution is that current frames for lightweight recreational backpacks add extra, unnecessary weight to the user's pack. To further clarify, low equipment weight is desired by many backpackers in the ultralight backpacking community. Our research shows that while this may be the case, many users still desire a frame in their backpack for effective load transfer from the fabric bag to their hips, as the packs will be used for long periods of time and carried over great distances. Thus, a solution for weight reduction while maintaining effective load transfer is to be desired. Our research shows that the weight of current backpack frames could potentially be reduced by implementing an advanced lightweight material in place of currently used light metals, such as aluminum. Many composite materials have a much lower weight density than lightweight metal alloys. For example, according to Dexcraft Materials, carbon fiber has a weight density that is roughly 54% of that of aluminum, meaning that the weight of a product could be almost cut in half for the same material use. Furthermore, most frames are currently made of metal alloys and/or plastics, and composite frames are scarcely found in the market for recreational backpacks. A few select frames have been recently developed utilizing partial composite sections, such as a small back panel which accompanies a larger plastic or alloy frame. However, the market for recreational backpacks lacks fully composite frames, and the fully composite frames that do exist on the market are specifically designed for hunting, firefighting, and other activities in which high load capacity of the backpack is desired. In contrast to this, ultralight backpackers only need to carry loads up to 30 or 40 pounds maximum, which can be achieved with a more lightweight frame. For frames to be used in this application, there exists a delicate balance between effective load transfer and acceptable frame weight. The ultimate objective of our project is thus to create a successful frame made of advanced composite materials, with the goal of achieving a decrease in frame weight through the use of lighter materials while maintaining mechanical quality. We set out to design a frame that would suffice in performance of mechanical load transfer while using a minimal amount of material. Following design of the frame, an effective manufacturing process was to be determined, and a mold design created for production of prototypes that will be made and tested. A cost analysis was performed as well in order to determine the economic viability of the new composite design. In order to achieve our project goals, we researched composite material science and manufacturing and discussed these subjects with a composites professor from the mechanical engineering department at Cal Poly to determine the best course of action. Possible frame geometries were designed as 3D models in SolidWorks, and details of the manufacturing plan were determined based upon the design for the frame. The expected weight of the frame was determined using mass property analysis in SolidWorks, and mechanical performance was analyzed using SolidWorks finite element analysis. An effective manufacturing process was then determined with consideration to the frame design. Mold design and creation remains in progress, and as a result, prototypes have yet to be manufactured and tested. Once created, prototypes are to be physically tested and evaluated for mechanical performance and overall weight. It was decided that the material to be used for the frame would be carbon fiber due to its high strength to weight ratio. In order to create a more lightweight and concealed frame, we decided on an internal frame style as opposed to external. The next step was to determine what the geometry of the carbon fiber internal frame would look like. The original design we created consisted of a frame built of hollow carbon fiber tubes, joined together in a roughly rectangular shape that would fill the perimeter of the backpack. This is believed to be potentially the best design option in terms of least material use, but was decided to be unviable due to the high level of complexity in the manufacturing process. The manufacturing of hollow carbon fiber tubes is a very complex process requiring advanced equipment that is unavailable to our team, and so we decided against the hollow tube frame for manufacturing purposes. The second alternative design we created consisted of a full-sized flat sheet back panel, with the option of adding corrugations to the outer edges of the panel to increase the bending stiffness of the frame. This option was determined to be viable from both a design and manufacturing standpoint, but was ultimately decided against because of weight considerations. The overall size of the frame would be too large, and the amount of material necessary to achieve the desired frame stiffness would cause the weight of the frame to be higher than anticipated. It was speculated that weight could be reduced in this design by cutting out sections of the frame sheet to decrease the total mass of the frame, which led to the third and final design. Chosen design of the frame is a slender sheet with dual semicircular corrugations running vertically on the outer edges of the frame sheet, and a slot cut vertically in the center of the frame to reduce the total weight. This chosen frame design is intended to be a composite version of comparable lightweight backpack frames which run vertically along the user's spine. The semicircular corrugations that run vertically on the frame's outer edges utilize principles determined in composite corrugation research in the Mechanical Engineering Department at Cal Poly and act like tubes to provide major increases in bending stiffness and load capacity. Additionally, the semicircular shape of the corrugations has no sharp edges which might cut into the fabric of the backpack or come into contact with the user's body, as opposed to, say, square or trapezoidal corrugations. The geometry of the frame has 15 degrees of curvature so as to better conform to the shape of the user's back, and is expected to be installed in fabric receivers along the center of the back panel, with padding keeping the frame from contacting the user's body. Thicknesses were chosen based on guidance from a composites professor at Cal Poly, with knowledge gained from his experience and previous experimental work with carbon fiber sheets and corrugations. For the style of carbon fiber to be used, a carbon fiber weave was chosen for the material so as to reduce manufacturing complications that may result from improper layup of unidirectional carbon fiber sheets. With the carbon fiber weave, the desired strength and stiffness is expected to be achieved while mitigating risks from improper manufacturing. The chosen manufacturing method for the frame production is a compression molding process in which mating top and bottom mold halves are used to shape the carbon fiber fabric into the desired geometry. The mold is to be made of machinable high-density foam provided at the manufacturing shops at Cal Poly and will be coated with a non-stick primer spray to allow for removal of parts from the mold. Production of parts will require a hand layup of the carbon fiber weave in the mold, thereafter painted with a mixture of epoxy and hardener and compressed in the mold with C-clamps or a compression machine and allowed to cure. A custom mold will be made with a CNC mill and thereafter used for production of the corrugations, while flat surfaces will be used to compress flat sheets for the frame sheet. The frame sheet will then be cut to the desired geometry and the corrugations will be attached in the proper locations with a high-strength adhesive. Finite element analysis of the frame design is currently in progress and is expected to yield results of acceptable load capacity and stiffness. 4 different loading cases have been considered for the analysis. Horizontal loading, as if the frame were in a backpack on the ground. Vertical loading, as if the user were tilting forward. Vertical loading, as if the user were tilting backward. And purely vertical loading for compression and buckling analysis. Expected frame weight has also been determined using SOLIDWORKS mass property analysis and published values of carbon fiber density. Expected frame weights are approximately 5.5 ounces for a frame with a 1/4 inch radius corrugations, and 6.7 ounces for a frame with the 0.4 inch radius corrugations. These are much lighter than the 11-ounce composite frame currently available in a hunting pack on the consumer market, and are expected to be lighter than a majority of alloy frames. Success of the manufacturing process and the performance of prototype models are yet to be determined pending creation of the molds. From an initial cost estimation, it was determined that the expected cost per frame for the composite design will be approximately $84, with a total backpack manufacturing cost of $124. For the analysis, it was estimated that the backpack will be sold at a price of $200, up from $140 for the comparison model. As a comparison, the new composite frame was compared to the frame used for the Kelty Red Wing 50, a best-selling recreational backpack that is very popular due to its moderate size and lightweight frame design, consisting of an aluminum beam and high-density polyethylene frame sheet. The expected cost per frame for this current design is approximately $17 per frame, with a total backpack manufacturing cost of $57 and a selling price of $140. These numbers show that because of the substantially increased cost to manufacture the composite frame, the current aluminum frame design allows for greater annual profit to the manufacturer. Further economic analysis is in progress to estimate the number of composite frame backpacks necessary to sell to break even with the profits from the current design, or alternatively, to estimate the necessary price at which to sell the composite frame backpack to make it economically viable. As shown by the cost estimation in comparison of the existing design and new composite design, it is not economically beneficial for the backpack manufacturer to implement the composite frame. It is thus not recommended that the new design be implemented, unless manufacturers are able to sell the new design at an even higher price point than estimated or lower manufacturing costs substantially. Additionally, it is possible that the manufacturer may be able to gain more market share from increased sales of backpacks that use the composite frame and potentially increase consumer base. In this case, it may be beneficial for the manufacturer to implement the new design. In the end, this project determined that production of carbon fiber composite backpack frames can serve as an effective way to achieve a lightweight frame design with desirable mechanical performance. However, costs for creating carbon fiber frames via compression molding and assembly are much higher than the cost to create alloy or polymer frames, and so backpacks with carbon fiber frames must be either sold in large volumes or sold at a much higher price point in order to make the manufacturing of the product economically viable. Further optimization of the design of a composite frame and manufacturing process could potentially be performed to make the process more economical for future models.